Welcome, ladies and gentlemen. This is your SN11 notes. At least I'm 99% confident it's SN11. If not, change it accordingly. I am doing this note guide by video simply because I am not here today. I am actually at a meeting in district office learning about something new, but I did not want to leave you, or I wanted to leave you in good hands, so I decided to teach this by video. We're going to be talking about the least squares regression line. Now, yesterday in the lab with the Skittles and Slinkies, you did find the least squares regression line using your calculator, and that calculator is an amazing tool. But I do need to make sure you realize how amazing it is by doing it long-handed. Much like when we did the standard deviation long-handed, you understand or understood the behind the scenes about the average standard deviation from the mean. And this is kind of the same thing, that it's important to know really where that least squares regression line is coming from. It's not just this magical formula that's being popped out of the calculator. The least squares, I'm going to just read from the top there. It says the least squares line or regression line for a set of xy data points is the line for which the sum of squared errors, which is residuals, we talked about that on Friday, or SSE, is as small as possible. So unlike the line of best fit, where you just draw your line in and try to follow the trend, the least squares regression line focuses on every single data point and minimizes the error using, of course, the idea of residuals. Properties of the least squares regression line, and this right here, folks, is very, very important. It says the fact that the sum of squared errors, or SSE, so you do need to know that right there. So sum of squared errors, or SSE, as small as possible means that for this line, these properties hold true. So what holds true? That the sum of the residuals is equal to 0. That is an important thing. So if your residuals are adding up to 0, that means you did it correctly. So this is a property for the least squares regression line. So if you have a least squares regression line, these properties hold true. Or if you have these, you can find the least squares regression line, as I'm going to show you very, very soon. The variation in residuals is as small as possible. Of course, that's what I kind of talked about at the top there. This third one is also extremely important. So I will put stars by kind of the key kind of points. The sum of the residuals has to equal 0. The line that contains the point of averages, which means that this point, x bar, y bar, is on your regression line. No matter what, it is a point that the line goes through. And that is, you'll see very, very quickly why that's so important. And then lastly, this monster right here, the line has a slope b, technically it's supposed to be b sub 1, where b sub 1 is equal to the sum of the observed minus the mean times the quantity of the observed minus the y mean divided by the sum of the difference in the x minus x bar quantity squared. And as always, those look very, very scary, but we'll break it down into a table. You can find the equation of the least squares line, this right here, by finding b sub 1 using the formula above and plugging in x bar, y bar, so the average point, to solve for the y-intercept b sub 0. I want to point something out. In all of your math classes, we've always written it as mx plus b. In statistics, for whatever reason, we feel a strong urge to flip the order of that, and we tend to write it as y equals b plus mx. And there is a rationale behind it, but I'll leave that for another day. Now, so if you look at this down here, right here, this y prime is your predicted equals b naught. So your b naught is your y-intercept. It's your initial start, plus b1 times x, and b1 is your slope. So it's nothing different than you've always seen. It just looks different. That's kind of a big point to bring up. So if you look at when you calculate regression, you have the choice of either picking y equals mx plus b or the y equals b plus mx. That's the reason why. It's just whether or not you're talking about an applied math course versus a statistics course. Anyway, so no further ado, let's kind of keep going. It says, example, find the least squares regression line. So least squares regression line is a long thing to write out, so we use this abbreviation, least squares regression line, of the following data. It says the table shows the cost per hour versus number of seats for 3 models of the DC-9 jet. Before I continue, I do want to say that this is in your textbook. This is the example. It's starting on page, oh, look at, I'm running over here to my desk. One moment. It starts on page 123 in your textbook and goes all the way through to 125. So if anything I say here, you need to have, to read it a little bit more thoroughly, please feel free to do that. Okay, so it shows the cost per hour versus number of seats of 3 model of the DC-9s. Now remember what we said the other day, that it's going to be Y versus X. That's again another statistics thing. When we title something, we tend to go the Y versus the X, or the dependent versus the independent. So this number of seats is the independent variable, so this would go on the X-axis. This would be the dependent variable. So I'm just reiterating something we talked about before. So the number of seats on the DC 930 is 100, cost is $17.50, and the 40 is 110 at $1,800 per hour, and so on. Notice that the averages are down here, so we do know that X bar is equal to 110, and we know that Y bar is equal to 1825, and that does play an important role as well. So this data is given to us, and in the textbook it's given to us as well. Notice it only has 3 points of data. That's for your sanity and mine, because this is obviously something we don't do very often. But again, it's behind the scenes of what your calculator is doing, which is important. It's important understanding. Okay, so use this table to organize your work as you compute the slope of the least squares regression line. So the first thing we're doing is we're taking, now remember again, this is X, this is Y. So we're taking the X minus the X bar. The X bar is up here, the Y bar is right there. So we have 100, this number right here, the X, minus the X bar, which is 110. And that, I'm going to erase this work. I just wanted to write it out so you can see where I'm getting negative 10. So if I go 110 over here, minus our average, and I'm going to put X bar up here so we remember that's right there. So 110 minus 110 is going to give me 0. 120 minus 110 is going to give me 10. The sum, so the sum kind of comes all the way across, is going to be 0. And I'm just kind of making sure you guys see where things are coming from. Okay, and by the way, the sum here, that's a good thing, of 0. Now, the Y bar, again, it's just on the top there, but I'm going to bring it down here so we have it right next to us. So 1750 minus the 1825, that's where what we're doing here for calculations. And again, just for space, I'm going to get rid of that. That's going to give us a negative 75. 1800 minus 1825 is going to give me a negative 25. 1925 minus 1825 is 100, and voila, when you add these together, it gives you 0, which is a very good thing to have. Now, notice over here, and keep in mind, folks, we're breaking this formula up here into pieces. So we've just done this component right here, and we've done this component. Now we're multiplying them together. So we are just breaking it down in steps. So I'm taking negative 10 times negative 75. So I'm taking my difference in my x's times the difference in my y's, and that's going to give me 750. So I'm really just multiplying the 2 columns together, or the row, I suppose I should say. Okay, it gives me 750 right there. 0 times negative 25 is 0. 10 times 100 is 1,000. And 0 times, well, actually, that doesn't mean anything. But we do want to add these together. When I add these together, we end up with 1750. Now, just again, to take a step back, if you hear the bell in the background, that is you guys starting to come to class, so I probably should speed this up. So we multiplied this and this together, and then we added them. That's what the summation's doing, right? So we added them together, and that's giving us, I already forgot, 1750, I'm pretty sure. Okay, so that top right now is 1750. I now need to find the bottom. the denominator. And that's that part right here, this very last column. So again, this is an important number right here in the formula. And we already have our x minus x bar, so I'm going to just use that where I'm going to square it. So I have 100, 0 squared is 0, 0, or 10 squared is 100. So I get a sum of 200. So folks, this is the interesting part. If we go back up here, so I don't mean to make you guys sick here, but really this formula, which gives us the slope, I mean, that's a big thing. This is calculating the slope. We end up with 1750 over 200. And I'm going to rewrite that also down below here. So I'm going to come on down and I'm going to convert it to a decimal. So calculate B1, which is the slope. It's going to be 1750 divided by 200. And I'm going to convert that over to a decimal, which gives me 8.75. Okay, so now I'm going to pause it while they do announcements. Hold on a sec. Okay, so what did I write here while I was paused? I wrote the regression equation, which is y hat equals b naught, which is your y-intercept, plus b1, which we calculated up above, times x. Now I'm going to remind you that this x bar, y bar, which is your average point, is, I'm just putting it right here so I can see it, it's 110, 1825. Okay. Now, not very different from what you've learned in algebra. I'm going to take this 8.75, which is my slope, and put it in for slope. And then I need to pick one point on the line to solve for my y-intercept. Oh, this point of averages is on the line. Why? Because that is one of the properties. So we can put in for y 1825. We're solving for b naught, which is my y-intercept, or our y-intercept, plus 8.75, which is our slope, times our x point that we know is on the line. Okay, you multiply this together, 1825 equals, you know what? You guys calculate it on out. I know you can do this, but just for time's sake, I'm going to let you know that b naught, or the y-intercept, is a magical number of 862.5. So our regression equation, folks, is y hat, which is our dependent variable, in this case money cost per hour, equals my y-intercept, our starting point, 862.5, plus our slope of 8.75 times x, which is the number of seats. If you were to put this in your graphing calculator and do a least squares regression line on this, this is what it will give you. Now notice my little side note there. Make sure you appreciate that graphing calculator. We will be using the graphing calculator in the long run, but for let's see, you're going to be working right now on P7. P7 is using this data, or this idea. So right now you're going to stop this video and you're going to do P7 and ask any questions you have tomorrow at the beginning of class. Thanks for tuning in.